All right, next RLC circuit here, guys, three-phase. This one looks like we have a Y resistive load. Right, these guys are all resistive circuits. This guy is our inductive circuit, and this is our capacitive circuit. So we have a Y resistive load, we have a delta inductive load, and we have a delta capacitive load there. Now, as soon as you see this with the capacitors in a delta, you know something's messed. Three-phase capacitors are usually connected up as a Y. That means that the voltage on the Y would be lower, and you could throw in a neutral there as well to deal with any unbalanced loads. It's not very often that you're going to see this capacitors in a delta, so we're going to probably see that the power factor is a little bit messed on this circuit. First step, though, is that we have 208 volts coming in, three-phase, right? So between any of these guys, we got 2 8-volts. Just like on all the other circuits, 2 8-volts between line 1 and line 2, line 2 and line 3, and line 1 and line 3. Okay, same voltage right across. Each of these loads, you can see here, are connected in parallel across those line conductors. So first step here is to bring the line voltage right across. Half the battle is knowing the recipe, guys. So you can see that we're following the same steps on each of these videos. 2 8-volts right across. Then you're going to keep track of whether it is a Y load, a delta load, or a delta load, right? So the Y load we're going to think of as, again, I've said this a million times, but we'll say it again, series circuit, right? That means that I line is equal to I phase. The delta we're going to think of as a parallel circuit. And so that means that V line is equal to V phase. Parallel circuit voltages are the same, and series circuit, the currents are the same. Let's draw this in properly. Beauty. Okay, so next step is for all the deltas, all the line voltages will be the same as the phase voltages. So this is 2 8-volts as well. Same with this guy. Right, you can see here that this is 208 volts. And this voltage across the capacitor is 208 volts as well. Okay, voltage stays the same in a delta. Now, with the Y circuit, this voltage from line to line is 208 volts, but this voltage from line to center tap is 120 volts. It is √3 less, right? So in order to find this phase voltage, we're going to take the 2 8-volts divided by √3, and that gives us 120 volts on the phase. Okay, next step, we now have the phase current, and on each of these, they're all balanced loads, so all of those are 41 ohms. Each of these loads are 28 ohms on the phase, and each of these capacitors are giving us 17 ohms of capacitive reactance. So next thing we need to do now is to take the, in this case, 120 volts divided by 41 ohms, and that is going to give you 2.93 amps. Okay, next thing we need is the, again, we're on step 3 right across here. So here we have 208 volts impressed across 28 ohms. 2.8 divided by 28 gives you 7.42 amps. Next one, we've got 208 volts divided by 17 ohms, and that gives you 12.23 amps. Next step, we need to take into account whether it is a Y or a delta circuit in order to find our line currents. So we only have one Y circuit here, and that Y circuit is telling us that it's a series circuit. I line equals I phase. So this current here, I line is equal to I phase. That current we found already at 2.93 amps. Okay, so again, keeping track of our currents, 2.93 amps. and on our line current, let's drop it in here, 2.93 amps. Okay, next thing we need to do is find the line current for the inductive delta load. Now, inside the circuit, we have 7.42 amps, but outside of the circuit, we're going to have root 3 higher. So 7.42 amps times root 3, and that gives you 12.85 amps. So outside of the circuit, 12.85 amps on the line. This line, and this line are all 12.85 amps. Okay, that is because each of the phase values are 28 ohms and all of our phase voltages are 208. Okay, next thing we need to find is the line current for the next delta. Now inside the circuit, our phase current is 12.23 amps. We need to find the current on the outside of the circuit. So that's going to be equal to 12.23 amps times root 3, and that gives us 21.16 amps. So this guy is drawing 21.16 amps on the line. Now, none of those currents for the resistive load, the inductive load, or the capacitive load happen at the same time. Okay? So next thing we need to do is find our line current. Okay? Our line current is going to be completely messed, because here you can see that the inductive load needs 12.85 amps. The capacitive load is usually just providing current for the inductive loads. It's there for power factor correction. Well, this guy needs 12.85 amps. This guy is providing 21.16 amps. Way too much for this load. So this 21 will feed the inductive load, and then because there's too much current, it'll actually backfeed on the lines, and it will go out and feed something else. So we're into a leading power factor here, where the current on this entire circuit is now leading the applied voltage. So that's a little bit messed, and we'll find that the power factor is poor as a result. Okay, we can also see that the the line current here is only 2.93, and then we've got disgusting currents on all the other components here. So line current here, we're going to take our resistive line current squared plus the difference between IL and IC squared, and then we'll take the square root. Now we're using the line values. Don't get screwed up and use the phase values. Okay, so if you take the 2.93 squared plus the difference between 12.85 and 21.16, let's draw that in here just so that nobody's messed up. 2.93 squared for the resistive current. And then the difference between IL and IC is 12.85 minus 21.16. So we're going to take the square root of everything. Okay, now this one here, you're going to find a negative value. Well, don't worry about that, because you're going to square it. You're going to multiply, a negative times negative is going to give you a positive number. Our total line current, when you find this value, is going to be 8.82 amps. Now, because there is so much capacitance in this circuit, that is going to be a leading current. Okay, last thing we need to do, that was step 4. This was step 5 in order to find our total line current. And then step 6 here is to find each of our individual power values. Anything all the way across the board is just going to be line voltage times line current times root 3. So we have 208 volts on the line. We've got our line current 8.82, and we're going to multiply that by root 3. That gives us 3,177.55. That is in volt amps. That's our apparent power. Okay, next thing we need to do is the resistive load, 208 volts on the line, times 2.93 on the line. And we're going to multiply that by root 3. That gives us 1,055.58. That's in watts. That's our true power. Okay, that would be our adjacent. So this line, this column right here is our hypotenuse of a right angle triangle. This is the adjacent, and the difference between these guys is going to provide us with the opposite. Okay, next thing we need to do is find our VARs for the delta inductive load. We have 208 volts. We're going to multiply that by our line current of 12.85, multiply that by root 3. That gives us 4,629.42. Okay, the units for that are in VARs. If you want to be specific, it's in VARs L. Okay, last thing here, guys, we got 208 volts times line current of 21.16 times root 3 gives us 7,623.24. Again in VARs, potential energy held on the capacitor, whereas this one is potential energy held in the magnetic field. Right, now if you wanted to double check these values, resistive current squared plus the difference between this and this squared, square root will give you a value that's very close to 3,177 VA. Last thing we need to do is to find our power factor. Power factor is watts over VA. So we have 1,055.58 watts. We have 3,177.55 VA. Notice here that we forgot to drop in these currents. This was our total current of 8.82. And finding our power factor using the ratio of the true power over the apparent power, or the watts over the VA. Let's check that out. We got 1,055.58 divided by 3,177.55 VA. Brutal power factor. Not even probably in the realm of possibilities, but 33% efficient. Okay? That is mostly to do with the fact that these guys are all connected up as a delta versus being connected up as a Y. Okay? One more time, so walking through this. Line voltage goes across. Phase voltage is determined whether it is a Y or a delta. Then you find your phase currents. Then again, using the fact that it's a Y or a delta, you're now determining your line currents. None of these currents happen at the same time, so we're using Pythagoras to find the vector sum of our line currents here at 8.82, and any value here is going to be line voltage times line current times root 3. Double check every values. This squared plus the difference between these guys squared, square root will give you a value that's close to that VA that's on the board. Alright, thanks guys. This one was number 5, so go on to number 6, and the next one will most likely be an RLC, but the capacitive load is going to be in a Y.